for our June Hangout. First, we're going to have Brian Akins talk about xhyve, and then we're going to have Brian Waldon up next talk about Kubernetes and CoreOS, and then after that, Matthew Garret talking about CoreOS security. So here we go.
So yeah, xhyve is a new open source project that is based on beehive from FreeBSD that has been ported over to the hypervisor framework that is in the latest versions of OS 10. So we've been doing some experiments and have some ideas on that. Just wanted to give a quick demo of that. So what we have here is an xhyve box that I've booted, and it is as simple as just running CoreOS xhyve run. What this will actually do is download an image and run it. Currently, right now, it runs entirely out of RAM, so it is stateless. But it is running the latest alpha, so that will run. I have one pre-baked over here. And as you see, it's just a normal CoreOS box. But one of the things that we can actually do is, for example, expose Docker to this so that we can then, for example, pull an image, an Nginx image, and once again, I already pulled it, then we can actually run that so that we see that we're running, and then we can actually hit that with curl. So, and then as you see, we're actually hitting the web app running inside of that. Why we think this is interesting is that it is a much more lightweight solution than some of the things that are currently in the community, and it's very interesting. We think we can package the runtime and the images in a single binary to download, and that gives interesting ways to distribute applications quickly to users to test. So.
Just kidding, you couldn't hear me. Up next, we're going to have Brian Waldon talk about CoreOS and Kubernetes. All right, guys. Waldon's having some technical difficulties, so for the time being, until he can come back, if Matthew Garret is ready, we'll have him talk to you about CoreOS security, and then hopefully Waldon can get back online, and we'll talk about CoreOS and Kubernetes some more.
Okay, hi. So I'm Matthew Garret. I work on security here at CoreOS. I'm going to be talking a little about the existing work that we've already shipped for improving container security, but also the work I've been doing over the past 2 or 3 months and that will be landing in CoreOS in the near future. So just let me find where that has gone. Why is this button not doing anything? I'm sorry, computers are basically terrible things. One moment, just let me stop presenting. Okay. The screen share button stopped working.
All right, we're going to try this one more time, having some difficulties. Sorry about that, guys. Why don't we wait a few seconds, see if it'll come back on. If not, we can jump back into our CoreOS and Kubernetes talk. Guys, happy Thursday. It's that kind of day. So let's try and go back to Brian Waldon for our normally scheduled Kubernetes talk. So let's see.
Okay. Hopefully everyone can hear me this time. MJG is back. I took. Oops. Okay. Well, hold on there a second, Matthew. I think I've got everything set back up on my side. Right. So I don't know what you heard when I was trying to say something earlier, so I'll just start back from the beginning. So Kubernetes, right. Kubernetes is a container manager coming out of Google. It's a tool that we at CoreOS have been really interested in over the past year. I think Kubernetes just had their 1-year birthday, so happy birthday to them. Kubernetes it's been developing quite a bit over the past year. It started with some really interesting ideas, and those ideas are kind of hard to swallow for some folks that may be more used to the well, I'll say old world, but maybe the current ways of doing things, and aren't ready to jump onto the bleeding edge. But we really love being on that bleeding edge and helping direct where things are going at CoreOS. So we tend to spend a lot of time with these sorts of projects and make sure that that we have a good understanding of what they're doing, but also have a chance to add our feedback where possible early on in the life cycle of the project. So I'm hoping today to sort of demystify some of what's going on underneath Kubernetes and provide a better understanding of how Kubernetes itself works. So not really looking too much at the really cool new flashy applications that you can run on Kubernetes, but looking at how you actually bring Kubernetes up on CoreOS specifically, but what subsystems you need to actually support the thing. So my little demo here is totally in the terminal. Hopefully the screen size is okay for everybody. I'm used to having to blow it up pretty large for meetups and things, but if we're all sitting at our laptops here, it shouldn't be too bad. All right, so just to get our bearings here, we have 2 VMs, Core 1 and Core 2. I have I guess I should show you one more thing first. Pardon me. Um, sorry if I get all inception-y here for a second. So I just threw this together, put it up on my GitHub repo. It's a really simple set of artifacts that that I'm using. These are all the scripts that I'm using, and like the actual systemd services. It automates the place that you actually pull binaries from to drive this demo on CoreOS. So if you're interested in looking at the actual source of what I'm doing, then please go to this repo. It's github.com/bcwaldon/Kubernetes demo. All right. So jumping back into my terminal. Oops, wait for it. There we go. So I have, like I said, 2 VMs. Kubernetes is obviously built to scale a lot further than 2 VMs, but for the sake of a succinct demo here, I want to just show 2, so you can see 2 workers and 1 controller, where the controller is sharing space on one of these VMs. So the first thing that we actually need to do to bring up Kubernetes is look at what its dependencies are. So the 2 major things are the persistence layer and the networking. So on CoreOS, we looked at Kubernetes very early on in its development. It was designed primarily to run on Google Cloud Engine or Google Cloud Platform. Yeah, I always get those confused. So it integrated directly with the more bleeding edge features in GCE. It sounds simple, but the ability to route an entire /24 network to a single VM. So obviously, looking at other cloud providers, you can do this with your own hardware with bare metal. But if you want to run this type of software on other cloud providers, there are some missing pieces. So going back to the persistence layer, the popular service on CoreOS is obviously etcd. So on these 2 VMs, I have etcd2 running. I'm actually just running etcd2 on the first node, and the second node is configured to use this first node as its etcd service. So very simple setup. Etcd has a clustering guide on coreos.com/docs, I believe. So deploying etcd across multiple nodes is just, well, I wouldn't say just as simple as a single node, but it's incredibly simple. But for the sake of this demo, I just needed 1 node. So for me, it was as simple as systemctl start etcd2. Actually, I guess I should take 1 step back here. I deployed these 2 VMs using this user data. So if we walk through this user data really quick, it's configuring etcd2 with the name called master. It's setting up setting up to bind on the private IPv4 addresses. This is the 172 network for those familiar with Vagrant, CoreOS Vagrant. And that's so I can route from the second node back to the first node for etcd traffic. So I've got etcd2 configured properly. I'm not automatically starting it. I wanted to do that manually, but I got a little bit ahead of myself in my demo, and it's already running. I turn off reboots, and this is not something you should do in production. That's the entire value prop of CoreOS is automated upgrades. But for the sake of a demo and knowing that we're cutting alpha releases pretty frequently here, I didn't want to risk my machine going down right in the middle of showing something off. Next is, and this is important for later, we're configuring Flannel to talk to etcd on this specific IP, and we're starting Flannel. Now, this is kind of a shortcut. This Flannel startup procedure isn't exactly quick, and we'll get into that here in a couple minutes. So I've also set up just a little helper -rc script so that I don't have to remember to run this command when I SSH into these VMs. So SSHing back in, oops, that's not a VM. 1 second. So I'm back on Core 1. Like I said, we have etcd2 running. There we go. You're all screaming at your screens just then with my typo. I wish I could hear you. etcd2 is up and running. You can see I started this 26 minutes ago, right when I was getting ready for this demo. And I guess that's etcd2 is actually the persistence layer used under Kubernetes. So solving the persistence problem for the Kubernetes control plane is as simple as turning on etcd2. So there are a lot of concerns that we have when we take something like etcd into production, like what happens when etcd goes down? How do you make sure it doesn't go down? There's clearly a distributed aspect that we're missing here, but that's sort of that's outside of the concerns of Kubernetes specifically. So moving on from etcd, jumping over to Flannel. So like I said, when Kubernetes started, it was dependent on some very GCE-specific features, like being able to route /24 to an entire /24 to a single node. Even in in EC2 Classic on Amazon, on AWS, you max out somewhere around 5, and that's for the largest of the instance types. So we wanted to make it incredibly simple to provide the networking requirements for Kubernetes, so that we could take Kubernetes and not just run it on GCE, but run it on any platform and not have to write code specific to that platform to make it possible. So on each of these nodes, I have a service called flannel D. Okay, I'm just getting silly. So I just ran systemctl status flannel D here to see what's going on. Actually, I'll run with -L so it doesn't chop off my lines. I can see that there's clearly a convoluted startup procedure here, and there's a lot going on, but once it actually comes up, it's picking a subnet in a specific range, and it's mucking with IP tables. So why is it doing that? What Flannel is trying to establish here is what we call an overlay network. An overlay network is effectively a virtual network running on top of an actual network. Now, your actual network could technically be virtual too, but it's just a way to distinguish between your overlay and the network that your actual hosts use for communication. So once we have Flannel running, it claims a subnet out of a larger network, and the way that you actually set that network is pretty simple. There's a lot more configuration that can go into this, but just for the simple case, we can look at this one script. So when I brought up these nodes, I ran this one command. This is an etcd-ctl, an etcd request, asking to store this data, this network config, at a specific location inside of etcd. Now, Flannel on both of these nodes, they're both configured to talk to the same etcd server, so they both share this configuration. And I basically just picked this network out of a hat as 10.244/16, because it doesn't really matter since this is a totally green setup. But you may have to pick this a little bit more carefully, depending on what existing decisions you've made for your corporate networking, existing product infrastructure. So going back up to the log output from systemctl status flannel D, it sees that it's picking a subnet in a specific range, and it chooses the .49/24 network. So this node has effectively chosen to be 10.244.49.x. And if we go look at the other node, it's chosen to be 10.244.66.0. Now, it's actually there's a hashing operation that happens on the local machine based off of the underlying host IP address. So it's very important when you're running on a platform like Vagrant to instruct Flannel how to identify what its host IP address is. And if you haven't run Vagrant before, that's because you end up with a set of devices like this. You have loopback, you have two ETH devices, where ETH0 says 10.0.2.15. And unfortunately, this is the network or the IP address assigned to ETH0 on every single Vagrant machine, at least that I've ever spun up. I may be missing something, but I, I probably would have got it by now. So we explicitly tell Flannel in the local configuration, not the cluster configuration. Let's just look here. In here somewhere. I'm sure you're looking at it right now. I don't know where it is. Well, I know how I set it. In user data, this line right here is very important. Flannel interface. This is telling Flannel what actual network interface to use. What actual network interface to use to identify what its local IP address is. And it can tell using a netlink operation what that is. So it happens dynamically at runtime. And this helps solve the race condition of Flannel starting up and too soon before you've actually configured your underlying host networking. Let me SSH back to this box. Oops, wrong box. All right, so we've got Flannel up and running on both of these nodes. They're both participating in the same overlay network, 10.244.0.0/16. Now, how do they actually communicate with one another? They both allocated a unique subnet. Now they need to be able to route between those subnets. So looking at this Core 1 machine, we see that it acquired the 10.244.49, and then down later in operation, it says UDP mode initialized, watching for new subnet leases, and it adds .66. And if you remember, Core 2 acquired .66. So not only are we using etcd for allocation here, we're using it for like updating the mesh. So now all of our Flannel nodes that are using or sharing an etcd service can keep track of one another. So we now have basically, I'll say a distributed overlay network. There's clearly a central point of coordination to achieve it, but that's not a hard requirement for the overlay network to keep operating. So we've allocated it, we've started tracking the other nodes in the mesh. Now if we, I guess there's one more thing to go through here. Before we can actually test this, Flannel's goal is to provide an overlay network, not just in general, but for containers. So the Docker mode of networking is to have a bridge locally that some network is assigned to, and let the Docker daemon actually allocate out IP addresses from a larger network. So if we run ipadder list, we have a Docker 0 bridge and a Flannel 0 network device. So the Docker 0 bridge is allocated this .1 IP address, so it can operate as a gateway, and Flannel holds the entire .49 network. Now, we bind this entire network on it, so Flannel can effectively ingest all of the traffic to this overlay network and send it off to the right place. Docker 0, it has to be configured with the .49/24, so it allocates out of the subnet for this specific node, but that's all Docker has to know about. It doesn't have to care how packets are actually getting between the larger /16 network. So we have our Docker bridge set up, which means we can now turn on containers that have virtual Ethernet devices on that bridge, and hopefully have those devices participate in this overlay network. So if I Docker run this BusyBox container, it's just going to sit here and sleep for 120 seconds, which is hopefully long enough to go over to the other node and run something. Docker PS, we have this container up and running. Docker inspect this guy. So we see that Docker thinks the IP address allocated is is in the overlay network 10.244.497. And if we run ipadder list, we see our virtual Ethernet device that's veth, but we don't necessarily care about having that IP address actually bound on Docker 0 or Flannel 0 or anything, since we have IP tables to clean up or to take care of everything. So Docker PS, we still have our container running. I go over to Core 2, where flanneld is running. IP adder list, similar to the other machine, it just doesn't have any containers running, so no virtual Ethernet devices. If I ping this container, Flannel handles routing all ICMP, TCP, UDP traffic to it. So at this point, we have the ability to run a Docker container anywhere across these nodes and have them able to communicate with one another. And this is a hard requirement for Kubernetes to actually work, as Kubernetes allocates a unique IP address to every pod. Now, Kubernetes, like switching gears here, we have etcd, we have Flannel up and running. What is Kubernetes doing on top of this? And I'm not going to go too deep into Kubernetes. I just want to touch on a couple of the core concepts, since I don't have a lot of time left here today. Kubernetes came at the container management problem, I'll say a little bit differently. I think we all know what IaaS is, or I shouldn't say that, infrastructure as a service, and what platform as a service are, or we at least have our own ideas of those, and we know something like Amazon Web Services or GCE or your bare metal like internal operations team is your infrastructure as a service provider. And something we could call a platform as a service is more like the git push deploy type workflow. And then there's this entire gradient between those two things, where you might have a dependency on some kind of resource that you wouldn't necessarily put in the infrastructure bucket, but it's more like a service that you need access to deploy your platform or your applications on a platform. So Kubernetes it's placing itself right between those two layers, where it's providing an abstraction on top of your resources so that you as the application developer don't have to worry about them, but it's also giving you the power so you're not forced to use some git push deploy workflow if you'd rather just turn on your services manually and manage them by hand. So just look through some of what Kubernetes is actually doing here. I think I said at the beginning, much of the feedback we've gotten about Kubernetes that we've heard from our customers, from our community members, is that it's big and heavyweight and complicated. The thing that I just showed you with Flannel is actually the most complicated piece, and that's not actually part of Kubernetes. Kubernetes is designed around a very decentralized workflow where we have a core master server or API server, which can now be deployed in an HA manner, so in a distributed manner. We'll say fault tolerant, just to be pedantic. There are other entities in the system that act on that API server, but all the API server does is hold data. There are specific kinds of data that other entities act with. Like you've probably heard of a pod. I might have said pod already, I don't know. The kubelet, the actual worker, consumes pod information and actually runs your containers, for example. The controller manager consumes replication controller data and creates pods. So it's all built around this shared workflow on transforming data objects into other data objects effectively, and generating new data objects based off of other data objects. So we can actually start with just the API server. I have it running here on Core 1. And it's been running here for 30 minutes or so. So the API server is up and running, which means I can run kubectl commands. Now, kubectl is the command line tool. Right now, it's the only tool you need. It's all API driven. The APIs are published using Swagger, so the bindings are actually dynamically generatable. What's the word there? I don't know. You know what I mean. So kubectl is just a little bit of sugar on top of these generated bindings. So if I run kubectl get services, see, I've got some data coming back. We haven't talked about what services are yet, so we don't know what this means, but I can interact with an API. Kubectl is hitting this port 8080 on localhost here to actually drive this interaction. Now, kubectl, yes, kubectl isn't really that interesting anymore. So kube API server, like I said, is just really just a data API. It doesn't do anything by itself. So the first thing we need is a way to ingest work and then schedule that work out somewhere in the system. This is a container manager, so we're probably deploying containers. To deploy containers, we need workers. I have 2 nodes here. Each one is operating as a worker. There's another component to the system. Like so far, we have kube API server. Well, etcd, flannel, kube API server. Now we have the kubelet. There we go, kubelet. So the kubelet is, again, just a client of the API. It understands how to watch for work that it should be doing and then to report back on that work that it is doing. So I have a kubelet running here on Core 1, and I have one running on Core 2. Yep, they're both up. So going back to kubectl, we can represent these workers as data objects. Maybe there's some dynamic aspect to it, but if I get nodes, node, kubelet, they mean slightly different things, but they're sort of interchangeable. At least I'm going to use them interchangeably here. You can see 2 different nodes, the 101 and 102. These are the 2 nodes that I have here running on my laptop, and we can see that the status is ready on both of them. In this case, ready means able to accept work. So I have an API server, and I have a set of workers. Sorry, an API server and a set of workers, yeah. Now, like I said, I'm going to keep saying this, API server is just a data server. It accepts data objects, doesn't do anything else with it. So if I create a pod, and we'll touch on that here in a second, a pod is a unit of work, then we need a scheduler. So something that actually takes that unit of work and places it on a machine. So we have a kube scheduler. Yep. So I have this simple thing running. You can see it's just configured to talk to the master. It's running on the blessed secure side of the network, so there isn't any authentication that I've configured or anything. And you could definitely do this in your setup, but I just haven't for the sake of brevity. So I have our API server, our scheduler, and I have some workers. So unfortunately, I didn't tear this environment down all the way, so I've already ran some of the commands that I wanted to run for you. But I would effectively run kubectl create -f pod, and when I run git pods, oh, maybe I haven't created it. Create -f. There we go. So I created something called the Redis master pod, and we don't even care what that is. It happens to be running Redis, but that's just some user's workload. So if I run kubectl get pods, and kind of decrypt this output here. Now the spacing looks all weird. There are good reasons why it looks weird. The first line is the pod data. The second through n lines are each container running within the pod. Now, this might sound kind of weird. We're running multiple containers as a single unit of work. A pod, this is one of the crazy ideas that Kubernetes engineers introduced us to when they launched Kubernetes, that you can have multiple, like the deployment unit isn't necessarily a container. You may want to group containers into logical units. So imagine you have a, let's say, a MySQL service, and every day you want to take, or maybe every 10 minutes, you want to take a backup. You could run 2 containers side by side, one that knows every 10 minutes, or maybe in response to a dynamic schedule, it has to pull a lock out of the database and actually package up a backup and stuff it somewhere in S3 or wherever. But it doesn't really make sense to schedule that as a totally separate application. So let's see if this was scheduled yet. Cool. Gotta zoom out. All right. So let's look back through this. We have a Redis master pod. It has an IP address now, and it has a host. Now, the host is the worker that it was scheduled to. So it happened to be scheduled locally to this machine that I'm sitting on Core 1. It's the .101, that's how I know that. But this IP address is actually in the overlay network. So just like I created a pod or a Docker container manually before, and I had a 10.244.49 address, I've now created an entire pod, which is a set of multiple containers that has a single IP address. So if I run docker ps here, I see a bunch of containers running. We have, let's look at this one first. So we have the pause container, which is kind of a weird name, and then we have this obvious Redis container. Now, when this pod is actually deployed, the way that we group these containers together is using, namespaces. Almost lost that. So Linux namespaces, and the really important namespace to have them all share is this network namespace, so that this IP address that we've assigned it, this 10.244.498 address, is shared amongst all of the processes running in this pod. So all of these containers can bind services to this IP address. So if I have multiple web services that are deployed as a single unit in a pod, I can address them all by the same network address. And just like we could before, if I go over to Core 2, the overlay network still works. It's the same exact primitive, but now it's assigned to a Kubernetes entity, where Kubernetes actually created the network namespace before it deployed the containers inside of it. So, and that's really the primitive for having this abstraction of your units, your units of work on top of the resources. This is how we get that next layer above the infrastructure as a service. And we now have a virtual network shared amongst all of this work, so that the actual things running the work can move around and not have to worry about what hardware it's actually on. And the one last thing that I wanted to touch on here before I hand it over to Matthew, so he can tell you about our upcoming security features in the operating system. It's the concept of a service. So a pod, like I said, is just a collection of containers. It's not really that interesting once you realize that, like, oh, it's just a list instead of a single entity. Where it really starts to get interesting is with services. So a service is another data object in the system. You create it with the API server, and another different entity actually consumes it. The kubelet doesn't consume it. There's a series of proxies that runs on each of the nodes to make services work, let's say. So I haven't actually tried to start this up yet in this demo. Let's just see what happens. Obvious one. I started up kube proxy. Now, just like we have a kubelet on every worker, we also have a kube proxy. So, oh, I lost my other one. Give me just 1 second here. I started up kube proxy on both of my my VMs here. They're both running next to the kubelets. So I'm going to create an entity called a service. Go find my data object. And again, all of this is in that GitHub repo that I showed you at the beginning. Gotta think straight. Share demo guest book. Okay. Just like I have a Redis pod, I also have a Redis service. Now, just create this service. I'm throwing it at the API just like I did the pod. Then I should be able to get services back and see, all right, so there's a new service here. There's something called a Redis master service. Now, a service is effectively a load balancer with a persistent IP address. Now, this is where things start to get a little weird. You see this this new third, well, not octet, you know what I mean. It's a different IP address. It's 10.100.163.43 instead of 10.244. something. Now, this is obviously outside of the range managed by Flannel. So what's going on here? So we've created this entity called Redis Master, and services is master. What's the command? Export. Oh, whatever. Just like the raw is here. I've created this entity, and all entities are represented by this sort of verbose JSON, but very like programmatically consumable JSON. We'll look at this. The first thing we need to look at here is the metadata. So we have this service. It's named Redis Master. That corresponds to the name output by the kubectl get services command. So there's our unique name. Then there's something called labels here. And then down a little bit further, we have something called a selector. So the way that we're actually tying entities together here inside of Kubernetes is by using a concept of labels and selectors that know how to query labels. So if we get pods, we have one pod running. It has a label, a name equals Redis Master. This is just an arbitrary key value pair. I'm looking at the service. Its selector is name equals Redis Master. So now we're starting to see a connection between these two things. The service, like I said, is a load balancer, and we're talking about networked web services here. So the obvious guess here is a load balancer that uses a selector across a set of labels to define its backends programmatically. Or dynamically is more accurate there. So I've created this service with a 10.100.163.43 address, and I'm on one of my workers here. And I really hope this works. It's not going to work. You're going to have to trust me on that one, unfortunately. I have I guess I started the kube proxy earlier. The kube proxy is actually, oh, there's your problem. My data models are messed up here. But we'll power through it. The kube proxy is actually responsible for routing this other network outside of the context of Flannel, or of your overlay network, your container network. So if I have two applications that I want to deploy, you connect them using this concept of a service. So you can deploy two applications totally independently without having to tie them closely together with configuration. And so you abstract it using this IP address provided by service. And it's outside of the network managed by Flannel, by the overlay network, so that that's free to be assigned directly to nodes and to be assigned directly to pods on nodes. So I think we've been able to go through some of the underlying components here of Kubernetes today. I will make sure I update the repo that I pointed at earlier with some of these notes, so you can kind of play with this yourself and maybe add a bit more of a README or a README, so you can bring this up with Vagrant. But like the goal here today was to hopefully help you understand what the major underlying pieces are under Kubernetes. So we were able to look at etcd and Flannel bring those like infrastructure services up so that we could deploy Kubernetes and actually get work running. And like if I weren't talking while I was doing all of this, then it would have been what, a 3 or 4 minute walkthrough. So hopefully that encourages the rest of you out there to actually jump in and start playing with Kubernetes and start realizing the power of it and start building some applications for it. So I think that is all I have for today. So I'll hand it over to back to Alex at Core HQ.
All right, guys. Thanks, Waldon. Next, we have Matthew Garret, who's going to be talking about CoreOS security. So I will hand it over to him.
Okay. There we go. Right, that's it. Okay, so my name is Matthew Garret. I work on security here at CoreOS. I'm going to be talking about some of the existing security work that exists in CoreOS and Rocket, and also the I'm sharing this again. Let's see. Is that any better? Anything? This worked in testing. Nothing. Okay. So, do you have me? Nope. Okay, I'm just going to quit and try to join.
All right. Sorry about that, guys. We're going to take a minute just to get him back online. Oh, there he is. That was fast. All right. So we shall try this again.
Okay. That looks better. Right, so starting this again, my name is Matthew Garret. I work on security here at CoreOS. I'm going to be talking about where we are already with CoreOS security in terms of Rocket containers. But then I'm going to be talking about work we've been doing over the past few months and that will be landing soon in CoreOS. So to begin with, we have the application and for administrators to have flexible management of the keys that they choose to trust. And this means that CoreOS systems can be configured in such a way that Rocket will only initialize containers that are signed with a trusted key. If the admin does not trust a specific key, then Rocket will refuse to start that container. And this means that even if a site is compromised, even if the container images on that site are replaced by a hostile actor, if the key has already been marked as trusted, the signatures will not match. The signature validation will not verify, and Rocket will refuse to start the container. So this way, as long as you have a mechanism for obtaining the keys in advance, you can trust that the container images you're running are the container images you expected to be running. You know that they haven't been tampered with by a malicious entity. But we're looking at going much further than that. The first stage is improving the security of containers itself. And this is work that's already been implemented by Red Hat and deployed in other contexts. And we're taking this and implementing it in Rocket now. svert is a means of running individual containers in separate SE Linux contexts. And each of these contexts is unique to that container. Other copies, even of the same container, will be running in independent contexts. If anybody is able to escape from the container or cause the container to misbehave in any other way, all they gain is the ability to tamper with or interact with files and services running as part of that components or cause code to be executed in other containers. This makes it much more difficult for a container breakout to be escalated into an entire system compromise. And we have this broadly functional, it's not quite ready to land, but this is code that is working, mostly validated, and will be heading for Rocket mainline in the near future. But going back to the idea of signed containers, like I mentioned, we have the issue that the keys need to be trusted. And right now, the keys are stored on the local file system. If someone is able to somehow get through the SE Linux isolation, if someone is able to execute arbitrary code on the host system, they are able to insert additional keys into that keyring because it's just stored on the local file system. So we're looking at reworking this and moving key management away from the file system, and instead pushing key management into the kernel, where it's possible to configure the system such that even root is no longer able to delete keys or add new keys to a keyring. And this will mean that at the point where a system's provisioned, a static set of keys can be injected, and the keyring then locked down. And from that point onwards, it's impossible for an attacker to modify the state of the keyring. That way, you can be assured that the keys that you are checking against are the keys that were there at initial provisioning time or boot time. Again, this code is now present in Rocket. We're going to be landing this as an optional feature to begin with, and we're going But if an attacker is able to gain access to your system, if they're able to modify the keyring on disk, there is a potentially more straightforward approach for them to take, which is just to modify the copy of Rocket on disk such that it ignores the keyring and just runs malicious code instead. We're taking Google's DM-Verity device mapper layer that Google use as part of ChromeOS, and we're integrating this into CoreOS. DM-Verity adds cryptographic validation to block devices. Each block is hashed, and there's a chain of hashes back to a root hash. If anybody modifies the file system or the underlying block device, those hashes no longer match, and the kernel refuses to perform the transaction. The system is then forced to shut down. This is well deployed, it's well tested, it's been used to defend against a large number of attacks against the ChromeOS systems. And the only real difficulty is that you need to have a mechanism to pass the root hash from an earlier stage up to the running operating system so the kernel knows what the correct root hash value is. And I'll be talking about in a moment why there are some subtleties involved there. Again, this is code that we now have running internally. It's code that will be landing in Git in the near future. And this is going to leave you in a situation where you can be assured that even in the event of a system compromise, it's still not possible for an attacker to modify the file system. It's not possible for them to cause the system to start running a different version of Rocket to the one you expected. That the kernel will actually enforce that protection. We're rolling out support for ensuring that this is the case by adding code for UEFI Secure Boot. UEFI Secure Boot adds cryptographic validation to the firmware. The firmware verifies that the bootloader is signed with a trusted key. The bootloader in turn verifies that the kernel is signed with a trusted key, and in our case, the bootloader will also extract the dmverity root hash from the kernel, from the signed kernel, and then pass that up to the operating system. That means that every single object in the boot chain is cryptographically verified. We have the firmware verifying the bootloader, we have the bootloader verifying the kernel, we have the kernel verifying the file system, and then once you're past there, Rocket from that verified file system will verify that the containers are signed with a trusted key. Any attempt to modify the bootloader or the kernel will result in the boot failing in a very easy to diagnose manner, as we then add additional restrictions such that the kernel will only load signed modules. We have some additional security hardening features that mean that it's not possible for an attacker to modify the running kernel. Now, this code is already in Git. If you want to, you can build a UEFI secure boot image from the CoreOS SDK, and you can experiment with that. We'll shortly be landing the dmverity code and tying that into there, and then we'll have the Rocket SE Linux code and kernel keyring code built around that. And what does this actually mean? And this is a full trust chain all the way from the firmware running code that I trust. This system has not been tampered with. But that's not where we're going to stop. We're continuing to look at ways to improve the security of containers themselves, and we're looking at especially making use of TPM hardware, for instance, to introduce cryptographically verified audit trails. It's going to be possible to say this system has run these containers, and we can prove that this system has not run any other container images. The benefits of being able to run Rocket on top of CoreOS mean that we can integrate our security throughout the entire stack in a very tight way. We can add functionality to the operating system and then take advantage of it in Rocket, or we can add features to Rocket that take advantage of the... if we want to add an additional feature to Rocket, it's very straightforward for us to add additional support code to the operating system in order to make that possible. So that's all that I'm going to talk about today, but I'm on IRC. I'm MJG59 on CoreOS and CoreOS Devel. If you have any questions about the security work we're doing, please do let me know. Thank you.
All right. Well, thank you guys. Thank you guys for joining us. I know there's a few technical difficulties in the beginning and a little bit in the middle, so thank you for bearing with us. We're excited to have all of you, and stay tuned for more Google Hangouts and meetups in your area. You can check out our community page. And all right, guys, thank you.